Let's make a start. Welcome everyone to this Methods Hub seminar given by Dr. Charles Rahal. It's my great pleasure to introduce Dr. Rahal as today's speaker. Dr. Rahal is a senior departmental research lecturer at the University of Oxford, where he's a member of the senior management team at the Leverhulme Center for Demographic Science, which is the largest demographic center in the UK, if not Europe. The center is unapologetically interdisciplinary, infusing knowledge and high-dimensional data from demography, economics, geography, genetics, statistics, marketing, business, philosophy, history, sociology, zoology, and Dr. Rahal's research prominently features in many of the high-impact publications, such as in Nature Human Behavior, Nature Genetics, American Sociological Review, AI in Society, and Population Studies. In addition, Dr. Rahal is a co-investigator at the ESRC Center for Care and is a steering group representative at the Reproducible Research Oxford. He has published on a wide range of topics, including developing new methods in sociology and econometrics, specifically on model uncertainty and machine learning, using unstructured data in social data science, scientometrics, social inequality, mobility and stratification, and civic technology. I'm delighted that he can join us today to talk about what can an open computational approach bring to the social sciences. So whenever you're ready, Dr. Rahal, please start your presentation.
Fantastic. Thank you ever so much for such a wonderful introduction. It's a real honor to be here at such a world-leading institution and the Methods Hub specifically. So as Professor Chandola mentioned, my name is Charlie Rahal, and I'm going to be talking about kind of a broad array of research interests, and specifically the underlying theme will be what an open and computational approach can bring to the social sciences. As Professor Chandola mentioned, I'm of course from the University of Oxford, where I work at the Leverhulme Center for Demographic Science, and many thanks to all of my colleagues and co-authors who will feature prominently in much of the work that I'll discuss today. So of course, it's a great pleasure to meet you. In general, I will mostly focus, as Professor Chandola mentioned, on creating new methods, on generating new data sets to answer both new and old questions. All of this will be done with a very open science perspective to make our research as reproducible and transparent as possible. And along with this comes a very specific interest in reducing uncertainty. This relates to how we kind of index our findings into the scientific record and how we can be sure of them and build on these ideas to advance science more generally. So within these kind of four methods that I like to use, the work that I do falls into five substantive areas. And these are the kind of the headers at the top of the slide that I'll talk about today. So the first is scientometrics, bibliometrics, and the sociology of science. The second is this intersection of civic technology. How can we use government data to create better policies? The third is to focus on inequality, especially within hidden unstructured data sets, and how we can kind of get a better analysis of what's going on in society. We already mentioned model uncertainties and either ways to reduce, eliminate, or how to represent our uncertainty more efficiently, more transparently. And the final one is kind of some work that I'm doing to develop new methods and techniques within the deep learning, the machine learning kind of infrastructure, and some frontier applications to these types of social problems with, cutting edge technologies, which I might be developing myself. So in the spirit of open science, the talks that the slides that you're viewing in this talk today are up online on my website, and all of the research that you see here today is on my GitHub page. So this is github.com/crahal. I also manage the Leverhulme Center's GitHub page, which is at Oxford DemSci. I also manage the Centre for Care's GitHub page, and I also manage another large centre's GitHub page, which is creating a new third sector database of all institutions within the United Kingdom. Throughout this talk, I'll frequently focus on what's next, and that is to say that I'll be introducing some of the things that I'm doing. I'll be priming problems and research questions. I'll be showing how I've answered them to date, and then I'll move on to the new techniques that I'm developing to answer new questions along these specific avenues of inquiry. So the concept of open science might not be familiar to all of us. So I've asked our dear friend ChatGPT, what is open science? Well, open science promotes transparency, most importantly. This makes all of our work open to other members of the academic community, but not only members of the academic community, also members of the general public who might be interested in kind of observing what academics are kind of working on. It involves the creation of scientific knowledge and making this available to other people. Importantly, it allows individual researchers to go and see exactly how kind of results indexed into the scientific record have been created. It allows them to query decisions that we've made along our kind of journey into creating results. And it allows them to then replicate and show what would have happened if they'd have made slightly different assumptions along the way. And one of the big things that I work on in terms of model uncertainty is generating a kind of entire holistic picture of what would have happened if we'd have chosen any other path of kind of inquiry along our process to getting a result that we might, publish in an academic paper or write in a blog post or given a presentation or otherwise. So this is a key kind of underpinning theme of all of the things I do. It's really important because this creates value by all of the things that academics do. It's only by kind of making our work available to other people that they can then build on it. It allows people to kind of go into the scientific record, this index of all of the knowledge that scientists have created to date, and query and confirm those results that have been ascertained. It allows us to kind of engage with academics and to engage with the public to kind of generate enthusiasm and kind of help others to recognize the importance of what we're doing. And most importantly, it allows science itself to become transparent. We want to have a really transparent scientific ecosystem because this is for the benefit, not just of the academy, but for all of the kind of the global population more generally. Ooh. And there's this wonderful, almost cliched phrase at the bottom of this slide. If I have seen further, it is by standing on the shoulders of giants. And this is a very famous quote by Sir Isaac Newton. And this is the kind of key underlying idea behind open science. By building on the work of those that came before us, we can kind of push on to the next generation of scientific inquiry. And this is something I feel really passionate about in general. Well, I'd quickly give some motivation as to why I'm so interested in this. And this was kind of forged in the furnace of a very hard-earned PhD, as all PhDs should be. And I specifically learned 4 really important lessons when I was a PhD student not too long ago. So the first is to make sure that all of your co-authors have code and that everything that everyone in a team of academics is doing is fully reproducible and transparent. So this is motivated by one specific instance where we had a paper get to an advanced stage of publication. And one of the co-authors on our team was unable to reproduce some of the work that they had done in the earlier parts of the paper. This meant that we weren't then able to make corrections based on recommendations from reviewers, and we were unable to be sure of what we had kind of already proposed as to being our headline scientific results. And this was quite an inspirational part of my learning curve as a student as well. We also want to kind of use open science, as we mentioned, to kind of query results that others have got. And I'll tell a very quick anecdote of a friend of my PhD program who said that they went to bed at night dreaming of having the stars pop up in their state of regression. And I thought, stars are important. We always want to get positive results because it makes the publication process more smooth. But with an open and transparent kind of pipeline, these stars, these p-values might not be as robust as they otherwise might have been. There was a very high-profile situation when I was a PhD student in about 2015, where a very high-profile paper, which was published in Science, had to be retracted because it came to pass that one of the PhD students who was involved in that paper had fabricated all of their data. And this only came to light when 2 other PhD students at an American university queried the origination of this data. And this was quite a dramatic affair that substantially kind of reduced the reputation of scientists in this specific area, much to the detriment of the entire field. Something that would have been avoided, of course, with an open and transparent process. And the 4th anecdote is about kind of my plea to use open source software. So when I was a PhD student, I was a very avid programmer, programming in many different languages. My PhD was in econometrics, so I was using languages like eViews and Stata. And my final PhD chapter was actually in a programming language called MATLAB. So MATLAB is an extraordinarily powerful software. So MATLAB is mostly used by engineers, but also by econometricians. When I graduated from my PhD program, I had a very nice paper ready to be published. It had a revised and resubmitted, a very nice journal. But unfortunately, because I had stopped being a PhD student, I was then requested to purchase an independent academic's license to use MATLAB beyond my PhD period. So this would have cost about £1,200 or so because I was no longer a student and I was no longer allowed to use my student licenses. And this kind of transformed how I began to think about software and free and open source software, FOSS, more generally. And this is something that, I might have been able to afford myself. I chose not to, but this would have hindered other academics who were less fortunate than I am. So if we want to be kind of thinking about making our entire research pipeline reproducible. We want to be doing it in open source languages that don't cost any of our academics anything to run because of whatever barriers they may individually face. As a bit of a disclaimer here, so I'm currently, as Professor Chandola mentioned, the local network lead coordinator for the UK's reproducibility network, and I sit on Reproducible Research Oxford. So I have a little bit of bias. There's some endogeneity there in that I self-selected into this role, but just as a disclaimer, this is something that I'm very passionate about, spreading the word about in general. To showcase the kind of the utility and the flexibility, as well as the transparency of these kind of tools, I'll show a couple of very quick examples before we move on to some substantive topics. The first example is this slide in LaTeX. So there might be some members of the audience here who are already accustomed to using LaTeX in their kind of article generation process or the process by which they generate slides. This little block of code on slide 8 here actually makes this slide. So if you were to copy and paste this into your LaTeX compiler with a begin document and an end document, this would have actually made what you see on the page here today. And this is to kind of emphasize the flexibility that open source tools allow us. I would show another very quick example in a similar dimension, and this is another snippet of code, and this bit of code is written in Python. So Python is usually my first choice of programming language. Whenever I'm beginning a new project, I'll typically begin to write it in Python. One of the reasons why I prefer Python and why I think Python is so important for the scientific ecosystem is because it allows you to do absolutely anything. That is not to say that there is not an enormous role for libraries and languages like Stata and eViews and MATLAB to play in the scientific ecosystem, but Python as a general purpose programming language, as opposed to a statistical programming language like R, allows us even further enhanced flexibility. So I don't know if there are any Pythonistas, any Python programmers in the audience today, if they've had a chance to quickly consider the Python code on slide 9, and if so, I would ask them to quickly put into the chat what they think this code does. What this code does, I will show you on slide 10. Whoops, there we go. So that very short bit of code actually creates this wonderful GIF of cats. This might seem like a very trivial example to show in such a well-attended talk, but I feel like it does a really good it makes a really good example of just the kind of the wide variety of things that we can do in Python. So with Python, we can build websites, we can build kind of dashboards, we can do very high dimensional data analysis, we can liaise with databases very easily, we can make extraordinarily high quality visualizations, and of course we can additionally do statistical programming just in the same way that we could have done in eViews, Stata or MATLAB. And importantly, it allows us to do a lot of things in this kind of new emerging area of deep learning and machine learning that is unfortunately a little bit more difficult, not impossible by any means, to do in eViews and Stata. But the way that Python treats its objects in the language is very, very, very flexible, as indexed by all of these wonderful cats on the slide. So I'd begin to talk about these kind of 5 key substantive areas that I like to work on and talk about some of the advancements that we're making, what is made possible with an open and computational approach, and then to talk about some of the exciting avenues which we're then going to kind of begin to consider over the next few years. If any of these kind of areas that I'm about to talk about are of particular interest to you, you would be more than welcome to send me an email, and I would be honored to collaborate if that would be something of interest to you. So one of the things that I'm particularly interested in is this kind of area of scientometrics. So I particularly like scientometrics as an academic discipline because it very closely relates to this concept of open science. Scientometrics, bibliometrics, and the sociology of science allow us to consider this scientific record, this index of human knowledge as we know and understand it, and then consider what has been done, by who, what directions is science moving in next, all usually at quite a high dimensional, at a population level kind of scale. And I think this is a really exciting opportunity that's really well facilitated by open and computational approaches, because we're typically going to be working in this area with kind of unstructured or semi-structured data sets from large bibliometric data providers that would have been a little bit more difficult to use in more traditional kind of statistical programming paradigms. Again, not impossible, but just facilitated by this computational approach. So scientometrics specifically is concerned with analyzing the science that's done. Bibliometrics is concerned with analyzing the metadata that is associated with all of these kind of pieces of scientific research. That might be a list of co-authors, a number of citations, an altmetric score, for example, the abstract. We could be doing some topic modeling on abstracts, which is something I'll talk more about in a couple of slides' time. And finally, the sociology of science. How does society kind of influence discovery, and what are the kind of sociological underpinnings of all of the advancements that scientists are making at usually quite a large scale? So a couple of examples to follow. One of the most prominent pieces of work that I've been very fortunate to work on with colleagues here at the Leverhulme Centre relates to genome-wide association studies. So a genome-wide association study is like a scan of all of the kind of variations in someone's DNA associated with a specific trait of interest. Historically, this could be a clinical trait. This might be a type of heart disease or cancer or something like this, but not necessarily related to clinical traits anymore. This is a really important kind of generative form of inequality that emerges from genome-wide association studies. And this was a key part of some of the past work that I've published and some of the work that I'm going to go on to publish. The reason why the inequality within genome-wide association studies is so substantial is because if we're to develop clinical cures, for example, on one specific population of interest, people of European ancestry, for example, the results from that genome-wide association study are usually only portable to others within that same population. This is quite important to study because the large majority of genome-wide association studies to date have almost exclusively been undertaken on people of European ancestry. So what we initially did is we took a list of all genome-wide association studies curated by the EBI, the European Bioinformatics Institute, and then we queried the PubMed API to get metadata on all of these individual genome-wide association studies and combine this with information on the ancestries within those studies. The first paper was a thorough scientometric review, and the second launched a substantial interactive dashboard, which kind of visualizes this inequality on a kind of real-time framework on a day-to-day basis. So we'll talk more about the dashboard in just a second. But I would quickly note here that the conduct of genomic work and how to do this ethically is of paramount importance and is something that we should never kind of forget. We should always keep at the forefront of our minds, and we should always make sure that the work that we're doing and the work that we're querying is always undertaken as kind of ethically and legally as possible. So a bit of fun here on slide 13. This is a frequency-weighted heat map of all of the keywords within genome-wide association studies. So we can see association in the middle of the double helix. We can see genome-wide and genetic and risk and variance and replication and things like this. But this is the kind of thing that we're talking about when we're talking about scientometrics and bibliometrics. Unfortunately, this figure didn't make it into the eventual paper, so I'm keen to kind of showcase it at any talks that I might give. But this accompanied a paper entitled The Scientometrics of Genome-Wide Association Studies with Professor Linda Mills, who I'm delighted to work on this stream. This is a screenshot of our kind of online interactive dashboard. You can find this at GWASdiversitymonitor.com. And as I mentioned, this kind of tracks diversity in GWAS participants, not just over time, but on a real-time basis. So when we first published the dashboard, I think this screenshot is taken from a good few years ago. Here we see that 84% of the participants in genome-wide association studies were of a European ancestry. If you were to go onto the genome-wide association diversity monitor today, you would see this number in the top left where it says 84.17% is now somewhere around 95%. So this problem is becoming even more kind of exacerbated over time as the kind of scientific inquiry into kind of genetic variance progresses, much to the kind of the detriment of those from outside of European ancestry populations. This is very much to do with the release of the large UK biobank, but there are emerging other large biobanks from other parts of the world, and we're very keen to see kind of how these trends emerge over time, and this is one of the motivations for making this tool that helps academics and genomic scientists and policymakers consider this kind of framework in this field more generally, all made possible by an open and computational approach. So this dashboard is built in a combination of Python and also a language called JavaScript, and specifically the D3 library. So I promised a good few slides on the kind of the what's next in this area. So I'm going to be pursuing a bit of research here that delineates this diversity in genome-wide association studies by who is funding the research. So the Diversity Monitor was a huge success. We've collaborated with many policymakers, with many NGOs, and we're always striving to generate as much kind of impact from the academic work that we can as is possible. So here what we're doing is we're going to again be using scientometric data, and scientometric data importantly contains some information about who funds the research. Some researchers are kind of mandated by their funder to include a diverse kind of variety of populations within their genomic work, and this is something that we're beginning to tackle within our genome-wide association diversity kind of strand of work. There are other forthcoming bits of work that might analyze things related to polygenic scores and how polygenic scores are made available to other members of the academic community. To very quickly talk about some other scientometric studies that I've been privileged to be a part of, we can also do things such as examining the gender disparity of authors within the scientific record. So the figure that you see here on slide 16 is a nice time series plot that kind of analyzes the proportion of authors within an esteemed journal called Population Studies over the past 75 years. So Population Studies recently had its 75-year anniversary. And we were invited to submit this scientometric analysis of all of the 2,000 or so papers that they had published. And we see this really big jump in the 1980s, where female authorship kind of begins to approach parity at 50% male and 50% female. We're not quite sure exactly what facilitates this jump. But this is something that, again, is made available with scientometric data and a bit of nifty programming. We can also analyze, as I mentioned, the emergence of topics. So here on slide 17, we look at the emergence of machine learning within the social sciences more generally. So machine learning has recently become quite popular, especially with sociological methodologists and other economists and other types of social scientists as well, for kind of solving some previously difficult to solve social science questions, because machine learning kind of offers us and affords us a whole new array of techniques with which we can kind of query things. So we quantified this. We were curious to know, is this this boom in machine learning and AI in the social sciences real, or is it just a function of the bubble that we were living in? And so what we did is we kind of generated a data set of every paper that had been written in the past 50 or so years, and we looked for different kind of mentions of keywords in abstracts and titles and things like this, and we were able to kind of plot this visualization that you see here. Importantly, one disclaimer with this figure is that we can't necessarily equate the mentioning of a term related to AI or deep learning with the use of AI and deep learning. So there might be some kind of fields within the sociology of science, for example, that are talking a lot about machine learning and AI, but they're not necessarily using it as a method in their kind of quantitative pipeline. But this is a quantification of all of the mentions of all terms and topics related to machine learning and AI within the social sciences over the long run. Ooh. So we're also very interested within the scientometrics kind of work stream with regards to the evaluation and the analysis of policy. So Hong Kong and the UK are very similar in many ways, and one similarity is that they both will have a kind of a regular review of all of the academic work that gets published by the universities within their remit, within the kind of catchment area that gets funding. So within the UK, this is called the REF. In Hong Kong, I believe it's called the RAE, the Research Assessment Framework or something like this. In the UK, it's called the Research Excellence Framework. And what we've been commissioned to do on this slide is we've been kind of questioned to analyze all of the impact that's being generated by all of the the universities, by all of the departments within the UK's kind of jurisdiction for funding. So we've called this work The Shape of Impact, which is going to be released quite soon, I believe. And here we're able to make a large number of statements about the type of impact that's being generated by academic work in this area. So for example, we can see on the slide here, visualization, that the larger a department is, it will typically almost exclusively be doing better, or be receiving a higher grade point average by the university's kind of grading schema within the UK REF 2021 framework. We're also doing kind of deep learning based topic modeling to see which topics are being analyzed by academics within the UK, stratified into kind of social sciences and physical sciences and medical sciences. And this is really exciting and illuminating work made possible again by a computational approach and some machine learning. Again, I promised some forewords about what we might be doing next. So we're trying to move away from analyzing specific journals or specific kind of number of impact case studies within a research excellence framework to consider the entirety of the scientific record in one holistic go. This is to look at every paper that's ever been written by every academic at any point in time. And we think this is really, truly exciting. And this is one of the things that I'm delighted to be looking forward to working on in the future. So we've come to an agreement with a data provider, a bibliometric data provider called Dimensions. And what Dimensions do is they're able to help us index all of the papers ever written. So that's their kind of role in our collaboration. They've got lots of scrapers that go to different publishers. They scrape data from Crossref, and they make this data available, usually only in very small kind of batches to individual researchers who want to analyze research done on one specific topic or in one specific journal. But we have permission from them, an agreement with them, to analyze all of their data at scale to consider the entire scientific record. And I've got a bit of an asterisk on the second bullet point here. And this is because there will always be some parts of the scientific record that will be impossible to index, a very, very, very small fraction, which might not be kind of caught within the kind of the big net of their kind of data scraping endeavor. So we think that we've got a large proportion of the scientific record, but perhaps not every single paper ever written, but we like to think it's comprehensive enough. And we've done a lot of analyses which show that this isn't biased in any specific way. And so this is going to power what I'm tentatively calling the evolution of Science Lab. And this is something I'm really excited about because it allows us to answer research questions such as how scientific ideas have evolved over the very long run. For example, some disciplines such as social data science that exist today might not have existed 100 years ago. There might be the emergence of new kind of highly impactful journals at specific points in time as a function of kind of policy or global events or kind of new academic ideas emerging from the fusion or the kind of delineation of individual disciplines. And so this is one of the key things we're looking at. We're also looking at how scholars migrate internationally over time. And this is kind of really exciting and important work. And there are definitely lots of kind of global migratory trends happening in general at any one point in time in human history within academia. And most recently and specifically, perhaps most proximally, the thing that I'm going to be working on most immediately, which we've already begun, is to analyze patterns in multi and interdisciplinarity. And we have an example of this on the following slide. So on slide 20, we have what we might call a figure 1, the headline figure, the first figure in the introduction to a paper which is kind of beginning to get off the ground now. And this looks at all of the 137 million papers within the kind of the scientific record as we're defining it, to look at how common is it for these papers in the left subfigure A to mention terms like multidisciplinarity or interdisciplinarity, and B, to analyze the average number of co-authors on any one specific paper. And this is related and important because interdisciplinarity has historically been measured in one way as being, let's say we have an economist co-authoring with a computer scientist. And this might traditionally have been termed as an interdisciplinary paper. Within this kind of work stream on the evolution of interdisciplinarity, we're working on what we think are kind of hopefully new, exciting metrics to kind of better capture what interdisciplinarity and multidisciplinary research really is and what it's doing and how it's formed and how it's evolved over time, using some exciting entropy-based measures. So this is one example of what's coming next, hopefully, in the evolution of Science Lab. Another one of my big substantive interests relates to civic technology and public administration. And I'm really kind of excited to work on this because administrative data is a little bit kind of new to the social sciences, but it's an invaluable resource for good. And there's some bias in this quotation on the slide because this is actually a quotation from the Administrative Data Research Network within the United Kingdom. So you might expect that they would be saying how great administrative data is. But this is something I sincerely believe in. The UK is especially rich in terms of openness of government data, and the value of this data is increasingly recognized. And this is kind of emerging in a new field of data science called government data science. For better or worse, I'm really interested in using this difficult, semi-structured or unstructured data. These are data sets that other people haven't been able to kind of wrangle and extract value from. This is where I kind of, I find great enjoyment and great privilege to work on this because I think there are so many exciting opportunities to take this kind of hard to use, unstructured data, which we might find in the wild, and then use the tools of open science and kind of computational social science to wrangle and clean, and then make this data available for scientific analysis or policy analysis or otherwise. So I think there are lots of exciting opportunities here. And I would quickly show a couple of examples about this type of data. So one form of data which I've historically been really lucky to work on is called procurement data. So in the UK, since 2010, it has been a policy for all UK institutions to make available line items of every contract which they settle for above a specific amount of money. So if we're a ministerial department in the United Kingdom, we need to make available information on that line item of spending to the general public. This is a totally new form of kind of semi-structured information, and it applies not just to ministerial and non-ministerial departments within the United Kingdom, but it applies to all hierarchies of government within the UK. So it applies to local authorities, to NHS trusts, to different types of kind of public institutions. And this really sounds like it might be useful for academic research, but the problem is that this raw data is unbelievably messy. And so many other data scientists might be kind of reluctant to approach or tackle this problem just because it doesn't typically come, the data doesn't typically come in the format that social scientists are used to. So we're not able to, download a nice clean tabular with row identifiers and column headers as we might traditionally be used to as social scientists, but that doesn't mean that it hasn't got immense academic value, which we're very keen to realize. So there are a number of problems with procurement data specifically. So some UK organizations don't believe in their legal obligation to make this data available, which we don't challenge. Every data set is available from a different institution, usually in a different place, in a different format. And so if we think that there are hundreds, if not thousands of different kind of institutions making this data available, they'll all host it in a different way on a different place. Very tricky to kind of wrangle and amalgamate. Data is commonly converted from a tabular file into a PDF. And so this is the bane of every good data scientist's life. So we really want to be using comma-separated value files or Excel files whenever we can. But some data providers are taking their tabular, nice spreadsheet row and column data and converting it into a PDF. So sometimes they'll even be kind of taking their Excel file and they'll be printing it out onto an A4 piece of paper, and then they'll be scanning that A4 piece of paper and then making that scan available on their website, which is an absolute disaster in terms of Sir Tim Berners-Lee 5-star schema for data availability. But we're going to do what we can. We're doing what we can in this regard. Naturally, of course, there are no unique supplier identifiers. So we're really interested in who's supplying these services, what amount they're supplying, when they supplied them, and looking for any patterns in this kind of data so as we can create value. A quick example of what this data looks like kind of in the field, in the wild. This is a CSV that was converted into a PDF. So we have to not only use a kind of custom built PDF parser to kind of get all of the information out of this, even when we get the information out of this, there are still lots and lots and lots of problems within this data. First of all, the expense area and the expense type, the fourth and fifth field, typically don't contain any substantive information about what's actually being spent, what the money is being spent on. The suppliers are often entered with lots of different names. So British Telecommunications might be called BT as their acronym, and we have to kind of reconcile these two entities within the raw data. Some of the amounts of the supplied goods are negative, which can happen, of course, if a rebate is generated, if a refund is given for services not rendered. Some of the negative numbers are purely a function of typing errors, which is another kind of battle that we have to grapple with. And there are lots more kind of different problems within this data. So we have a pipeline of research here, which kind of is able to find, download, parse, clean, and then reconcile the suppliers in order to generate value from this raw data. So some examples of what this kind of can be used for in the kind of academic sphere would be, we can see which ministerial departments are spending their money on kind of which SIC codes. So SIC codes are different classifiers of types of industry. So we can see, as we might have expected, I think in the leftmost column in the heat map, the DFT, the Department for Transport, is spending the majority of its funding on construction. So this is the Department for Transport, unsurprisingly, is building kind of railways and motorways, highways, and things like this. So this is just one example of what we can do with data from the ministerial and non-ministerial departments. Another example, a keen research interest of mine, relates to third sector organizations, to civic society. And so we were really interested in kind of what the role of civic society is in healthcare provision. And so here we were able to get data, again, in this really messy PDF format, from all of the different NHS, the National Health Service organizations within the United Kingdom. And again, going through this process of scraping, cleaning, reconciling, and so on and so forth, we can see that the majority of services that are supplied within the National Health Service within the UK are done by what's called super charities. There's these extraordinarily large charities that kind of operate very, very, very similar to large businesses. And it's not so much these kind of small kind of grassroots organizations that we might have otherwise hypothesized. And so we have a paper here, which is currently a revised and resubmitted a reasonable journal, and this is one of the main findings that we proposed there. One of the GitHub pages that I kind of convened, that I showed on one of the earlier slides, relates to the generation of a new database of all third sector organizations. This is really kind of essential work, because defining third sector organizations is something really hard to do in different kind of geographical jurisdictions. There might be different kind of requirements of how a third sector organization registers, but within the United Kingdom, this is very hard to measure. And so some organizations might be on different registers, some might be under the radar. And so we're working with colleagues from all across the United Kingdom to build a new and comprehensive database, a kind of a register of all third sector organizations that can be used not just by kind of charities themselves, but by policymakers and by academics interested in civil society. We have another example of what this data makes possible within the National Health Service. And so here we can see the increased involvement of private sector entities within the National Health Service. And this is done as a function of the Health and Social Care Act of 2012, which attempted to make a more competitive market for healthcare within the United Kingdom. Oops. We have some work related to the COVID-19 pandemic, where here a very curious thing happened within the United Kingdom, in that while unemployment rates went up, while employment rates went down, the number of people registering new companies kind of increased substantially. And we thought this is quite interesting, a really interesting hypothesis to test. Is this people being made redundant from their job and are they then going and starting new kind of bedroom businesses, as we might call them? Or was it kind of people who had existing companies in the Companies House register kind of taking advantage of the new opportunities that the COVID-19 pandemic made in terms of kind of setting up new companies, perhaps with government support or otherwise. A kind of the next step in this kind of field of work using Companies House is to kind of examine some of the inequalities in company ownership across the whole domain of all UK companies. One of the final things that I would discuss quickly in terms of kind of civic technology or public administration would be regards to a data set which we've currently negotiated access to, which is a data set on every test of every car within the United Kingdom on an annual basis since 2005. So this is called an MOT certificate. So every year a car needs to have a test which certifies its road safety and the emissions that it generates, where it's registered and things like this. And it contains hundreds of millions of observations. And we think there's lots of work here that can both merge civic technology, public administration, and also inequality. So we're set to answer a range of questions with this data set over the next 5 to 10 years, such as what are the effects of unregulated exports? Within the UK, there are lots of requirements on what a car needs to do to maintain its roadworthiness and its emission standards. But these requirements slightly change if you want to export this car outside of the United Kingdom. We might hypothesize that there are kind of intersectional characteristics of pollution generation within cars. It might be that some kind of people are generating lots more pollution with more powerful cars. Other people are using more kind of environmentally friendly electric cars, for example, or hybrid cars. And we're also interested in using this data from a kind of population studies type of perspective to see whether we can generate enhanced estimates of internal migration, because we have information on the owners of all of the vehicles, and we can see where these vehicles are being registered and how these kind of vehicles themselves as a proxy for their owners are migrating in an internal kind of ecosystem. So to quickly move on to some of the inequality research which we're looking at, and what's going to be done next, facilitated again by a computational approach. We're traditionally interested in using unstructured raw data again. There's lots of existing and very high quality sociological and economics work specifically on kind of socioeconomic inequalities. We're kind of moving beyond these traditional boundaries of using survey data sets to kind of observe large scale genealogical data, again, found in the wild. So I'll talk about a couple of very quick examples of what we're doing there. So we were able to kind of scrape a database of something called Who's Who. Who's Who is a kind of an international registrar of all professional elites. We were specifically looking at Who's Who within the United Kingdom. And here we were able to analyze something called the Old Boy Network. So the Old Boy Network is this kind of concept within the UK. If you go to an extraordinarily kind of prestigious high school or secondary school, you then kind of leverage your social network connections to kind of ascend the professional ranks into legal institutions or into hedge funds, finance or things like this as a function of kind of your background and your network. And we showed that while the Old Boys Network has very much kind of declined over time, it does still persist. We're interested also in this kind of legacy of longevity. So we analyzed a wonderful genealogical resource called the peerage.org, which kind of allows us to get information on the genealogies of all kind of British peers, British aristocrats. So these are earls and lords and barons. And importantly, we're able to analyze their lineages. So we're able to analyze their children and their grandchildren and their great-grandchildren to analyze what their life expectancy was in comparison to members of the general population, perhaps as a function of their wealth and their status, or their ability historically to have more highly nutritious food and things like this. What's next in this kind of inequality domain is that we're looking at something called probate data. So again, this is going to be leveraging our skills of parsing PDFs. And what a probate is a record on death, which gives information about the person who is deceased, and importantly, all of the assets that they had at their demise, and how they then bequeath this to their offspring, but not necessarily so. They could have donated this to anyone that they saw fit to do so in their will, in their kind of last testament, their last testimony. And so we have information from all of the probates in the United Kingdom from 1858 to 1996, and we've already scraped these. We're pre-processing them, ready to get them. We're cleaning them up. We're kind of scraping off all of the little bits of dirt and the dust because these are all scanned, of course. We're making them ready for OCR, optimal character recognition, so we can pass this data that you see on the left-hand side of the screen into more familiar computer readable, machine readable tools that we can then analyze at scale. Our idea then is to build life tables and stratify this by the amount of wealth at someone's death. And this is a really exciting bit of research, again, with Aaron Reeves and Naomi Muggleton, co-authors here, who were also co-authors on this wonderful, the Companies House paper on COVID a couple of slides back. One other thing that I'm interested in terms of inequality research, this leverages my interest in social care. So I'm a co-investigator on the ESRC Large Centre for Care here, as Professor Chandola mentioned at the start of the talk. And I'm motivated to do this work because I sincerely believe that social care is very quickly becoming an international crisis. This is partly due to aging societies and aging populations. And importantly, a large majority of social care is provided informally. This is usually done by family members, but not necessarily. It could be provided by friends or neighbors or volunteers. And there are different costs associated with providing this type of informal care. I was specifically interested in this area of research and how we can calculate the causal effects on these costs. And calculating causal effects in a intersectional framework is quite difficult. And so what we're trying to do here is we're developing improvements in the existing synthetic control literature. And so here we're fusing machine learning techniques into inferential research designs. And so this allows us to create a synthetic version of a person who may or may not have provided care to somebody, and then we'd have calculated what would have happened to that person's life trajectory if they hadn't have provided care. This is a very clean causal identification problem, and it can be used with granular data such as censuses, biobanks, or otherwise. This is important because it allows us to operationalize costs, not just as financial, but in terms of educational opportunity costs, for example, or different types of costs. And so this is a really nice way to merge machine learning with more traditional causal inference techniques within the social sciences. So I think I'm coming on to one of the final two substantive topics in the talk. As I mentioned at the top, I'm really interested in this concept of open science and the scientific record. And there are really close links between open science and traditional modeling paradigms. Machine learning is traditionally thought of as being a bit of a black box in that, we put some numbers into our algorithm and it gives us some things out at the other side. I would argue that to some extent, this is also true of more traditional statistical modeling pipelines. For example, we might have a wonderful piece of published research which calculates a beta coefficient, and in a paper of interest, the beta coefficient might be 7.12452. How do we know that this is really what the beta is in reality, that this is a true reflection of this causal or associative estimate in the real world? I was most motivated to begin thinking about this from a really wonderful paper published by one of my academic heroes, Professor Edward Lima, in 1983, when he himself was only recently graduating with his PhD. And he wrote a really informative and influential article called How Can We Take the Con Out of Econometrics? If you didn't want to read that paper, there's a wonderful podcast on a podcast network called Econ Talk, where Ed Lima is interviewed 35 years or so after he published his article about what changes he thinks have happened within econometrics as a function of his really illuminating perspective. Well, my suggestion as to how we can take the con out of econometrics is naturally, transparency and more computational procedures. I'll give a very quick example of how I think that this works. So say we have our friend, the researcher, on the left-hand part of the screen. Our researcher friend is going to ask the question, what's the association between y and x1? They want to know what the coefficient of the beta hat, for example, associated with x1 is. Is it really 7.12? When they're building their linear model, they might ask themselves, should we include this covariate x2? They decide yes. They then go for lunch with their academic friend and they ask their friend, I'm building this model, y equals alpha plus beta 1 x1 plus beta 2 x2. Should I include x3? And their friend says, no, that's not theoretically motivated. We shouldn't be including x3 in your model. And the friend is thinking about it, the academic is thinking about it a little bit more later in the day. And he's thinking, well, should I include this variable x4? And he decides, yes, theory that I've read recently makes me think that I should be including x4 into my modeling pipeline. The next day, he's thinking, should I include x5? And he's not really sure. What about if this researcher had chosen to include x3? If he includes x3, should he then include x4? If he includes x4, should he include x5? And you can perhaps see where this is going. He then initially decides not to include x2. How does this then change all of the decisions that he's making along his garden of forking paths, as Andrew Gelman kind of famously calls it? And we see that now this researcher, while honest and earnest in his kind of enthusiasm for doing theoretically motivated work, could have perhaps arrived at a large number of different models simply by including 4 additional covariates. There are lots of kind of bits of work that I'm doing that help us think about this, that kind of visualize the uncertainty of all of these different choices that our friend the researcher could have made. But specifically over the next few years, we're building a new library in Python and R called NRobust. And the idea of NRobust is to advance the specification curve literature. So the historic specification curve literature would kind of make a visualization of each of the coefficients that could reasonably have come out of a model based on theoretical choices. So some theoreticians might have said that we should be including x3, but some might not have been. So there we have 2 different models, both of which are feasible and reasonable to consider. However, the existing specification curve literature is perhaps slightly limited in that it doesn't, while considering the feasible output space, this is a really important thing to note in that it's not purely data mining for the sake of data mining, that it's limited in that it doesn't consider kind of posterior features of the model building process. So it doesn't consider anything to do with model selection, which of these models best fit the data. It doesn't consider model averaging. Maybe we want to put weights on each of the different models. For example, if we look at our researcher friend here, it might be that models with X5 in should have a higher weight than models which don't have X5 in, for example, and we can kind of approach this with model averaging based econometric techniques. We don't do any cross-validation or bootstrap resampling in terms of kind of seeing how our results might have varied if we'd have had a slightly different input sample. And so here we're kind of working and motivated again by the CARE framework to kind of validify, verify many of the kind of academic results indexed into the social care literature, which have enormous consequences for policy, as one of our examples, but not just within the CARE framework. We think that this is going to be of broad utility to a range of different kind of academics, both within and outside of the social sciences, by incorporating lots of exciting new features and functions into what we're calling the next generation of specification curves. Again, only really made possible through the utilization and implementation in kind of computational tools and techniques such as R and Python. One other thing that I'm inordinately interested in most recently that I hope to be publishing on soon is this really important idea of pseudo-random number generation. So the methods hub at HKU is a wonderful place to talk about this work because I might be able to ask the audience participants a question here today. So has anybody in the audience ever ran a program twice and had a different result each time? This doesn't really happen if we have a deterministic algorithm, like a linear kind of estimator. But if we have any kind of other estimator, which might have more than one local minima or maxima, which the optimization function is considering, we might have a different result every time we run the program. You might have observed this phenomenon, and you might have realized that what you need to be doing is setting a seed in your kind of algorithm. And by setting a seed, we can ensure that our algorithm gives us the same number out every time we run it. And this is the kind of the current best practice in how we think about variation in stochastic algorithms, which are instantiated with a pseudo-random number generator. So we might have been setting the seed to eliminate this variation. However, in our forthcoming perspectives article, we're arguing that this current best practice across the large majority, if not all, of scientific practice is in fact the exact opposite of what we want to be doing. We think that academics and scientists outside of academia even should be kind of considering all of the uncertainty that's generated as a function of all of the different seeds that we could have put into our algorithm. So say if we put in set.seed123 and we get our beta1 is equal to 7, and we do set.seed 456, and now our beta1 is minus 7 for whatever reason as a function of the algorithm that we're using. By setting the seed equal to 1, 2, 3, we're ignoring all of the possibilities that the kind of output space of our algorithm could have generated for us. And so by putting into the scientific record, by publishing a paper, with setting a single seed to eliminate this variation, we're saying to other scientists who might be looking to build on our work that we're showing that beta1 is equal to 7.12 or whatever. And this is quite problematic. And so we're arguing not only that this is extraordinarily important, this is extraordinarily prevalent and common across a large majority of kind of computationally complex workflows, but not just limited to computational workflows, to a large number of kind of more traditional social science modeling paradigms, for example, with regards to imputation or bootstrap resampling or otherwise. And we're attacking this with lots of different kind of replication projects. So within the paper, I think we have 7 or 8 different replications of really high profile, well-published papers in some of the world's leading journals, and showing just how substantially these results can vary. So within the machine learning literature, there is a little bit of work in this area. And in machine learning, there are lots of different sources of how the seed can affect the output of an algorithm. One of them is how we fold the data. So in machine learning, we'll typically fold our data into different partitions, and we'll train our model on all but one of the partitions and test our model on the other one. And then we'll partition our data in a different way and test on a different one until we've trained and tested our model on all partitions of the data. However, depending on how we set the seed to randomly partition our data, the average performance of our algorithm can vary substantially. So on the leftmost plot here, we have an application in Nature Medicine, which tested the efficiency of diagnosing someone with COVID based on their symptoms alone, where we could say that the ROC-AUC is as low as 0.7 or as high as 0.8. In a middle plot, we have a more kind of canonical data set where we don't look at the effect of folding, but we look at how random forests are instantiated. And on the right-hand most example, we have an example which tries to do optimal character recognition on the famous MNIST data set. So it has, this is how kind of postal services know to send your parcel to the right place, because the address bar, and when it's written by hand, will go into a scanner, and then the machine learning algorithm will kind of read the address from a handwritten bit of a label. And here, depending on how we instantiate and fold that model, the results can vary quite dramatically. Out of 10,000 samples, we can get, I think, 9,998 of them correct, or only 9,200 of them correct. And so the variation caused simply by setting the seed is enormous. And while in these examples, it might not substantively change the fact that the algorithm is roughly accurate or not, it does change how we index results into the scientific record. There are, of course, lots more examples relevant to the social scientific community. So on the left, we show how kind of different variables could be resampled within a specification curve framework. And on the right-hand side, just in case there are any time series econometricians in the audience, we show how the price of Bitcoin might be forecast with a random walk. And random walks are kind of a function of a draw from a random normal kind of distribution. And depending on how we set the seed, we could be forecasting that Bitcoin is going to be as high as 100,000 US dollars a coin, or as low as $3,000 or $4,000 a coin, simply as a function of how we set the random seed. And this is important in time series econometrics because the random walk is often used as a benchmark for more advanced models. It could be an ARIMA model, it could be a DSG model, it could be any other type of model that's able to generate time series forecasts in general. There's one specific paper that's a great inspiration to me called the Fragile Families Challenge, published in PNAS by Matt Salganik and colleagues in 2021. And here, this is perhaps the most familiar example to social scientists in that the substantive results of this paper vary quite significantly based on how they're setting a seed, not to do any types of prediction, but on how they're kind of multiply imputing missing data within their algorithmic pipeline. And so this is a function of how the seed is set in a stochastic imputation algorithm in R called Amelia. So what's next in this domain? What do I think kind of computational and open science practices make possible here? Well, we're thinking to make an index of seed variability. So we're thinking to set up a repository where people can do one of two things. They can examine how seeds have been set in existing published pieces of work and kind of report on the variation caused by this seed. Sometimes it will be very substantial, and sometimes the variation caused by seed will be very small, depending on the kind of parameterization of the research algorithmic pipeline. And we'll also be allowing people to kind of pre-register a project. Well, they'll write a kind of pre-registration report and they'll submit it and they'll index it and they'll get a DOI. And then we generate not just a seed, but a large number of seeds for them to consider in their algorithmic pipeline. There might be kind of some members of the audience here who are saying, well, it's very computationally expensive to run an algorithm 10,000 times or 100,000 times to kind of see the variation as a function of seed. But this is where high performance computing in the social sciences kind of really has a great deal to offer, because it makes running kind of computationally intensive and expensive procedures a large number of times very, very feasible, especially given how powerful high performance computers are becoming in the present era. And so the final of the 5 substantive things I would quickly discuss would be related to machine learning and deep learning specifically. So in addition to being interested in STS, science, technology, and sociology, technology, and science, STS, I'm also an active kind of deep learning, machine learning researcher myself. So I have a long-standing interest in forecasting and prediction. This is my background is in computational time series econometrics. But here I'm keen to apply it much more frequently to kind of more pressing social science problems rather than time series econometrics. This work typically comes in the form of developing new methods and metrics, and the application of these metrics and other frontier level techniques to social problems. So one thing that I was very keen to be a part of was the development of a new kind of evaluation metric, a model evaluation metric, which need not be as a result of a machine learning kind of paradigm, which could be used in kind of any social science kind of modeling paradigm, where we take 2 predictions of a certain thing, a baseline and an enhanced, where a baseline prediction could be as simple as the prevalence. And then we make some kind of complex calculations to set these 2 predictive systems equal to each other based on some principles of entropy. By kind of setting the entropy of the 2 systems equivalent to one another, we're then able to calculate something which we're calling the intermodal Bigorish, which tells you a dollar amount that you would have been better off, that you would have received if you'd have used one model over another. So say if we have one model which is trying to predict the outcome of a COVID test, for example, and then we're simply using as the baseline of that kind of problem the prevalence of all COVID tests at one point in time, we would then be able to say that our predictive model generates 17 cents on the dollar, for example, if we'd have used that instead of a baseline prevalence. And it's this kind of direct model comparison that I think is really missing from the kind of social science methodologists toolbox and how we evaluate models in general. We're also interested, as I mentioned, in kind of using open and computational techniques to kind of see what's possible in a deep learning and predictive framework. So we have a piece of work that's just gone online recently that takes essays written by children age 11, their polygenic scores, and teacher evaluations to see how accurately we can predict things such as their educational attainment later in life. Again, coming back to this kind of concept of social care and the increased need for methodological advances in this area, I'm currently working with some city councils within the United Kingdom to leverage what's known as technology-enabled care data. So technology-enabled care data is information on people who receive care. Are they leaving their front door open late at night by mistake? Are they boiling a kettle several times within 1 hour? And by using this kind of high-frequency real-time sensor data, we're hopeful that we're able to generate alerts in real time to predict the future demand for urgent care. So this would be able to create a positive intervention for somebody who might in the future need to call an ambulance, where we would be able to send a care worker to provide assistance. Maybe their blood pressure is high or something else. And it's by leveraging cutting edge technology combined with advanced methodologies that we're able to kind of advance societies for the social good. This is extraordinarily preliminary, and that we're still in the process of undertaking and kind of understanding all of the ethical and legal aspects to this work, and more generally kind of understanding the ecosystem of how all of these pieces of data on a care recipient and a care provider kind of all fit together, and whether this is even possible. This is very kind of prospective, kind of blue skies type of thinking, but we're hopeful that we might be able to provide kind of some technology to improve provision of social care in this area. We're also kind of interested, finally, as you might have guessed, in this kind of index of social prediction. So social science methodologists are kind of becoming increasingly interested in kind of how predictable things are. Not least within a health and social care kind of context. How accurately can we predict that someone is going to have a fall? How accurately could we predict that someone is going to have a heart attack in the future? And how can we leverage deep learning and machine learning technologies to kind of enhance, with a view to positive interventions, this type of infrastructure ecosystem? We're kind of curious as to how much irreducible error remains. So, for example, with the prediction of heart attacks and cancers, for example, just how accurate can we be? How close to the limit of perfect prediction can we be in the future? This is as much a philosophical question as it is a kind of practical methodological one. And one kind of exciting idea that we're kind of working on as a team here is how we can incorporate a large number of signals into the kind of the potential risk for cancer into a model. So traditional the Framingham kind of indexes might have only used the number of cigarettes smoked per day or the level of exercise taken. But we think that there's an SWOS type of approach, a social-wide association study type of approach that can leverage thousands of variables, either within a large longitudinal study or within a census or within a biobank. And each of these kind of individual pieces of information, these variables, might contribute a very, very, very small number of predictive power, but their contribution of information is positive nonetheless. And how can we leverage all of these really small signals without kind of overfitting any model and getting around traditional problems of overfitting in a kind of linear framework to create as accurate predictions of things like heart attacks or cancers as possible? Importantly, we want to kind of think more and do more about how this research can be undertaken ethically as well. So I think that's all of my 49 slides. To conclude, I would thank you all immensely for attending. There is an open invitation for anyone interested to please contact me at the email address on the slide with a view to any potential collaborations. I'd be delighted to discuss anything that we've discussed in the slides or otherwise. I hope I've been able to confer my enthusiasm for all things related to open and computational social science here today. Thank you ever so much again.
Thank you so much, Dr. Rahal. I really enjoyed that. I'm sure many of my colleagues and people online also enjoyed that. So we have time for questions. So Dr. Rahal, if you don't mind, stop sharing your slides so we can see a few more people. Yes, we definitely have time for questions. I'd like to open the floor to anybody who'd like to jump in, wave or raise your hand, or type in the chat if you'd like to remain a bit more anonymous. While my colleagues are being shy and thinking about their question. Oh, we do have one from Patrick. Yeah, go ahead, Patrick.
Thank you so much. Really, really exciting presentation. And I guess the thing with open data is it's kind of a project. And I think it's one that folks like you are really pushing successfully, and I think have been won over, I'd say, in the past 2 years of my own research. But with that in mind, maybe in 5 or 10 years, all social science will be open, and in that case, someone looks at your presentation today and they see maybe a generalist, like a complete generalist. So I want to just give you an opportunity to maybe frame how you kind of see your work fitting together beyond kind of this open science approach, which again, I'm very sympathetic to.
Yeah, so you mentioned a wonderful question. You mentioned the concept that all research might be open in the future. This is the dream. This is kind of one of the key things that I'm hopeful to do today, is to encourage anybody who hasn't been converted to this kind of open science framework, as you clearly have, to kind of to encourage them to get on board, because I think that's the direction of travel. And if we can accelerate this in any way, then that's something that I'm very keen to be a part of in my daily practice as an underpinning theme of all of the things that I do. So in terms of my work fitting into this, I think that one of the things that I'm specifically contributing with regards to the civic technology and the public administration is that we're making new data sets available. So all of the procurement data that we make, that we kind of process, we put available online the data sets before we even have a preprint of the paper up. And so this is something that I'm hopeful will change kind of quite dramatically in the future, in that currently and historically, academics have perhaps been a little bit more closed in how they share research data. The kind of general philosophy would have been, I've spent 2 years building this data set, I can get 5 papers out of this, so I'm not going to share this data set until the 5th paper is published and I've got all of my 4 stars ready for the research evaluation type of thing. And this is something that I'm hopeful will change. In addition to all data sets kind of gradually being open, data sets will become open as they are created and as kind of a design of the research themselves. So when research is funded from whoever the funder might be, there should be, without being controversial, there should be mandates on when this data can be made available and how it can be made available. So I actually took out one of the slides I had about this at the start of the talk, about how kind of new repositories such as Zenodo and the Harvard Dataverse have kind of gradually increased in their popularity and prevalence over time. And kind of my work fits into this by the provision of many data sets, and these have all got, you know, kind of minted DOIs associated with them. And these all kind of emerge as byproducts of the research to enable other academics to do research on those data sets, sometimes before I've even published a single preprint on any of them myself.
Thank you. Any more colleagues with questions? Please don't feel... Oh, we've got a question from Frank. Frank, please go ahead.
Hi there, Charlie. This is an amazing talk. I really enjoyed it. Especially your your science of science research is very interesting. So a couple of weeks ago, I was at a conference in the US, the Academy of Management, where some old colleagues of mine from Northwestern University were talking about a disciplinarity or interdisciplinarity penalty for scholars who are working interdisciplinary, find less or are less likely to get tenure, are less likely to be cited. Your work is all over the place, right? A lot of topics there. Is this an issue? Should we worry? What do you think?
Well, this is both an academically and a personally difficult question. So I think it's so insightful. So in the work that we're doing on interdisciplinarity, we're not making any comments specifically about whether interdisciplinarity is good or bad, whether it has positive outcomes or negative outcomes on the trajectory of an individual academic or on the advancement of science themselves. What we're specifically interested in doing is creating new metrics and methods for analyzing how interdisciplinary something is or isn't. To give a more personal answer, I was kind of brought up within the UK infrastructure of kind of research funding. I was very fortunate for my PhD to be funded by the Economic and Social Research Council here, and then I've had many grants by them. And the ESRC within the UK specifically, and this relates a bit to my talk on the role of funders in research and open science more generally, is that the ESRC has always pushed interdisciplinarity, and that's a kind of political position that they've always taken, that they think that interdisciplinarity is a positive thing about how we can integrate ideas from kind of different kind of areas and different methods. Specifically, we have lots of genetic work in the social science, for example. We have lots of deep learning in the social science, for example. And so I think that there is a research policy question as to whether it's beneficial. In terms of whether it helps an individual academic's trajectory, I think that there's lots of research that would say it does and some that says it doesn't. It's something that I believe in, naturally, as you might imagine, given that my talk is one of the most interdisciplinary talks that I could think of by design. I find it personally enriching to work on such a large number of projects with so many different and varied academics. And I think that my own work has contributed to how others do their work, and their work has similarly contributed to how I do my work. And it's this kind of cliched Newtonian quote that we're standing on the shoulders of giants, but the giants could take any format. They don't have to be in one academic discipline. Maybe in Newton's case, he's only drawing on other mathematical giants. But in the social sciences, I think specifically we have so much to learn from colleagues in other departments from where we might be individually employed, I guess.
Thank you very much, and I agree, Charlie. Well said. Thank you.
Thank you, Frank.
Thank you, Frank. Terry, would you like to go next?
Oh, yes, I just want to follow up with Frank's question. So because I still try to understand what academic discipline you were from, right? So do you see yourself more as a sociologist, economist, or so we for example, anytime when you like it when you land university, right? For tenure-like job, we need to find an academic department to host you. So which academic department do you think you will feel more comfortable in if you were, for example, in HKU?
So in general, I identify myself as a social scientist, and that's probably not a satisfactory answer by any admission. My undergraduate degree was in business. My PhD was in, my master's and PhD was in economics. I then worked in social policy and public administration, and then in public health, and then in sociology. All of the kind of papers I've published and the things I'm working on, the preprints that are coming out, are in an array of different disciplines. I find each of them have got their own important kind of problems. The underlying theme, of course, is that these problems, I think, can be tackled with computational problems. So there's an emerging kind of academic descriptor, as it were, as the computational social scientist. And I don't necessarily think that the computational social scientist needs to be pigeonholed specifically into one discipline because of the things that, the question that Frank raised. The computational social scientist, as a member of an academic team, can learn and leverage from academic specialists and contribute their kind of computational skill set to those individual problems. Every kind of good data scientist needs to have, a bit of mathematics and statistics, a bit of programming, and then the third kind of thing in the trinity is substantive domain knowledge. And so while I'm kind of an expert to a small extent in a large number of different fields, a lot of my work is co-authored with people who are, deep sociological theorists, for example, or they might be experts in theories related to social care and social administration. And so these kind of co-authorships that I seek to leverage and kind of brand myself as the computational methodologist, a social science methodologist, albeit a little bit vague, is kind of how I see myself. And I think now there are lots of specific degrees, terminal MSc programs, for example, in computational social science, which are emerging. And I think probably in the future, in the next 5, 10, 20, 30 years, the computational social scientist as an entity in themselves will perhaps one day be recognized in the same way that a sociologist or a geographer might be. With regards to what substantive questions they tackled, I think that remains to be seen in the future of this very rapidly emerging field. I'm not sure if I answered the question. Yeah, no, I'm at home in any number of social science disciplines. I think, again, being very vague.
Thank you, Terry. We definitely have time for more questions while my colleagues are thinking about that. If I could jump in with a slightly long-winded question. So I really hear what you're saying, Charlie, about the sort of the lack of diversity in a lot of GWAS studies. So UK Biobank famously is meant to be representative of the 20 largest cities, but only 5% ethnic minorities in the data set. It's not very represented, although I definitely remember UK Biobank people saying, well, it doesn't have to be representative in order to do good causal estimation and so on. You can get a causal estimate that doesn't have to be representative, so the size clearly matters. So but I just following on from that, you mentioned the term data in the wild a few times, and so I'm just probing you a little bit on that term, because some of your examples I thought didn't quite fit the diversity elements that I was looking for. So, for example, looking through records on who's who, or looking at people who own vehicles, or looking at people who have wealth to pass on in probate. These are not exactly people who are poor. And so my challenge to you is what do we do in order to find data in the wild on people that are much larger than rich people? Maybe it's not easy. Should we if we can't find enough data, should we use weighting procedures to sort of weight the existing cases, or what are the solutions to finding more data on underserved populations?
This is an extraordinarily challenging question, not just for me, but I think for anybody working in this area and how their research kind of shapes up. So one of the key definitions of data in the wild, perhaps, would be that the analyst, the academic who's doing the study, is not the originator of the data. And so the kind of data origination process is perhaps the problem with how the data is generated, what the DGP is. When I undertake this kind of data in the wild type of work, I will always seek to undertake the work on a representative sample. Sometimes the bias within these samples is a representative bias in that the population of people is biased. So the ascent into who's who in the UK is traditionally of white older males. And this is a fact of the population. This isn't a sample. And so my response, although perhaps is slightly insufficient because the DGPs in some of the data generating processes in some of these situations is insufficient, is that you would analyze where you can the population of people. So some of the analyze where you can, the technology work that we do with the peerage, for example, looks at the offspring of all of the aristocrats within the United Kingdom of the past 550 years. This is a biased sample as a function of the fact that the peers themselves are biased. They are wealthier. The peers are historically, before the 20th century, 94% male. And it's only recently that peers in the House of Lords have become more female. And I think that my answer would be that we would always look at the population of things where we can. And if there is a bias, that's a form of inequality that we can analyze and comment on and seek to redress in future data generating collections. So to bring this back to the start of the question with regards to the UK Biobank, there are an extraordinarily large number of studies, as I'm sure you're aware, about this bias. So this bias is not just in terms of ethnicity or ancestry, it's in terms of its predominantly higher socioeconomic status, higher income, more predominantly female, it's more geographically segregated and not representative of parts of the country in general. And so when we talk about diversity in genome-wide association studies, we talk about diversity in things that we can affect prospectively and how we're collecting data in the future. And when we're analyzing historical archival data, if there are biases that are a function of that historical social inequality, that is something that we can comment on, analyze and contribute in a way that kind of hasn't been done before, in that the majority of the in the wild things that we do are for the first time and, are answering questions that haven't been able to have been answered sufficiently historically, I guess.
Thank you so much, Charlie. So if does anybody have any more questions? I think we're it might be time to say give a big thank you to Dr. Rahal. I really, as I said, I really enjoyed that. I'm hugely impressed with your ability to transcend across different disciplines. I note your expertise in computational time series modeling. I mean, that your econometrician background is a highlight. But in addition, you have all these other disciplinary and cross-disciplinary skills. So it's very, very impressive. So on that note, I'd like to thank you so much for this wonderful presentation, and hope we get to see you soon. Thank you.
Thank you again for the invitation. A real pleasure to meet you all, and thank you for your time.
Sure. Bye-bye. Bye-bye.